You may have heard of Greek scientist and mathematician Archimedes, who, as legend has it, needed to determine if the king's crown were really made of gold, or if a cheaper material had been substituted. Since density is equal to mass divided by volume, and a different material would have a different density, he needed a way to find the volume of the crown. One day, as he was lowering himself into his bathtub, he realized that the water was rising around his body. And if he fully submerged himself under the water, then the amount of water displaced was equal to the volume of his body. This caused him so much joy that he leapt, naked, out of the bathtub, and then ran through the streets, still naked, crying "Eureka!" Now, I'm not about to strip, as it is currently 35 degrees out. And I also don't have the actual man Archimedes or an actual bathtub to demonstrate this in. But I do have these plastic babies and a bird bath. So here we have a baby, and I will be putting this and many other babies into the bird bath. The problem here is that you'll see in a moment when I put the babies in, the water level doesn't visibly rise. So in a moment, I'm also going to go get a rock and put that in. But anyway, if I were able to measure the volume of the risen water, then it would be equal to the volume of all the babies that I had put in. And this makes sense, right? Because if I put a material that fully filled up the bird bath, aka it had the same volume as the bird bath, then all the water in it would have to go somewhere else. It would be displaced. It's easier to lift things when they're underwater, because as soon as you start to lift an object, it starts to be supported by the water beneath it. This is called the buoyant force, and it's basically the water equivalent of placing an object down on a table. The table pushes up, and so does the water beneath an object. But we can tell that if the object is sinking, it must be trickier than the table example. It's easiest to start by imagining the water by itself. The water on its own has a certain amount of pressure, and this pressure gets higher as we descend because it has to counteract more water weighing on top of it. At any point in the water, we can imagine the weight of all the water on top pushing down and the buoyant force pushing up. To make sure the water stays still rather than swirling and sloshing around, these have to be equal on all sides. When we put an object in water, the pressure and the forces of the water at each of those points is the same as before, so the object will float at whatever position the buoyant force equals its weight. As you can see, this has to be equal to the weight of the water it displaced, because it's basically just standing in for all those water molecules that used to be there. So at the end of all that, the buoyant force of these babies as they sink is equal to the weight of the water each one of them displaces. Archimedes, too, would feel a buoyant force as he sank, equal to the weight of the water that spilled out of the tub. This is useful if you're trying to get an object to float, or if you're trying to change your depth underwater. If your submarine weighs less than the water displaced, then it'll float, and if it weighs more, it'll start to sink. Submarines and fish adjust their depth by controlling the amount of air inside them. More air in the ballast tank or the swim bladder will make the object as a whole lighter. And on a final note, ice floats in water because as it turns into a solid, it expands, and that means it has to spread the same amount of weight across a larger volume. So that's going to make it have a lower density than the liquid water. So as you can see, it's going to float in the liquid here, right above our beautiful babies. Now, I am going to stop handling ice and go inside.